What makes IIR filter design different from analog? Imagine trying to recreate the sound of a vintage radio using a digital device. How do you make digital filters behave like real-world analog components? That's where IIR filters come into play. In the world of signal processing and control systems, IIR stands for Infinite Impulse Response. These filters are designed digitally but aim to mimic the behavior of analog filters, which are built with physical parts like resistors, capacitors, and inductors. Unlike analog filters, which work with continuous signals, IIR filters process signals that are sampled at discrete time intervals. The main difference starts with how they are built. Analog filters relying on physical components whose values can change due to temperature, aging, or manufacturing tolerances. Digital IIR filters, on the other hand, use mathematical equations stored in memory. These equations involve coefficients that define how the filter responds to input signals. Because these coefficients are stored digitally, they stay consistent over time, making the digital filters more stable and predictable. Designing analog filters involves calculating the right component values to get the desired frequency response. For IIR filters, engineers often start with an analog prototype, like a Butterworth or Chebyshev filter, and then convert it into a digital version. This transformation is done using techniques such as bilinear transformation or impulse invariance. These methods help preserve the characteristics of the original analog filter in the digital domain. Stability is another key difference. Analog filters are usually stable if designed properly because they use passive components. Digital IIR filters can become unstable if the feedback coefficients are not chosen carefully. Also, analog filters can be designed for linear phase response, which means the signal's shape is preserved. Digital IIR filters tend to have nonlinear phase responses because of their recursive structure, which can distort the signal's phase but often improves efficiency. Speaking of efficiency, IIR filters are computationally less demanding than other digital filters called FIR or finite impulse response filters. They need fewer coefficients to achieve a sharp frequency response, which means less processing power. This makes IIR filters ideal for real-time applications like audio processing, communications, and control systems where speed and resource use matter. Performance-wise, digital IIR filters can produce very precise and repeatable frequency responses because their coefficients do not drift over time. Analog filters are more susceptible to component tolerances, which can cause deviations in performance, especially at higher frequencies or for complex filter designs. In practical terms, IIR filters are used after signals are converted from analog to digital, such as in audio systems, radio receivers, or digital cameras. They help clean up signals, remove noise, or shape the frequency response. Analog filters are still important at the front end of systems to prevent aliasing before digitization. To sum it up, IIR filter design is about translating the behavior of analog filters into a digital format. They offer advantages like stability, consistency, and efficiency, but requiring careful design to avoid instability and phase issues. This makes IIR filters a vital link between classic analog filter theory and modern digital signal processing techniques in electrical engineering.